Hello, how are you? This is your usual lecturer, ANG. I'm here today to teach on a topic, limits and continuity. It's also a subtopic from the ones we have listed. So today we'll briefly consider what limits and continuity is. Now we'll consider limits first. If time permits, then we consider continuity. But if there is no time, then we consider continuity in our next clips or class. Now, for the sake of this class, we're going to consider limits and continuity. But as usual, the mass, the code is the same, calculus. Calculus. Today's topic is limits and continuity of a limits and continuity of a function. Now, what is limits? Let me continue with this. When we say limits, we are saying that something is tending to a particular point. Something tending to going towards a particular point. But before that, I wish to tell us that the concept of limits is essential and fundamental in the study of calculus. The concept of limits is essential and fundamental in the study of calculus, as calculus remains necessary in determining the rate of change. Now, as I have earlier stated, limits, when you say limits, it's more of like going towards a particular point, going towards a particular point. But before I dive into it properly, let us quickly talk about some terms that we'll be making use of. Now, let's consider this. This is an expression. Now, this expression means x approaches a. This means x approaches a from the left. X approaches a from the left. You can see that the upper part here now we have a negative sign here. It means x approaches a from the left. Or you can also say x tends to a, the point A, from the left. From the left. Now, these two things means the same. So, as I earlier said, when you say limits, we are talking about something going towards to a particular point. So, these expressions are the things that we will be seeing often. Now, if we say x approaches a from the left, let me further describe it using a graph so that we will underline it. Assuming this is the real number line, then say here is a point A based on the information that I have here. Then this is the left part of A. This is the right hand side of A. Now we are saying that we are interested in all x values that are on the left side but very close to A. So think numbers that are here very close to this point A. All x values that are on the left hand side of A. All x values that are on the left hand side of A. That's what it means. All x values that are on the left hand side of A. Now, if that is true, then let's say let our A be equal to 2. If A is equal to 2, then based on that graph, this point here will be 2. This point here will be 2. And we said we are interested in all x values that approaches A, very close to A. All x values that are on the left-hand side and very, very close to the point A. And very, very close to the point A. Very, very close to the point A. So we are all, if A is now equal to 2, then we are indirectly saying that we are interested in all the values that are on this left-hand side, which are very, very close to 2. Now, on this right-hand side, after 2, in increasing order, you have 3 and so on. But on the left-hand side, meaning that you have about, let's say if here is 1, here is 0, then very close, it will be 1 point something. We are talking about just say 1.9 is very close to 2. One can also say 1.99. One can say 1.8. If you say 1.8, that is also close, though a bit far as compared to this and also this. Then one can say 1.999, then 1.9999. You know, all these ones are very close, but not on the point 2, but very close to 2. So as I earlier stated, I said when you're talking about limit, we are talking about something going close to a particular point. So when we say this on the left, this, where meaning that we are considering those points on the left hand side that are very close. So meaning this one will be 2 this, 2 raised to power this negative sign. That's what we have. Now, if I haven't gotten this, what if the sign here changes? If the sign here changes, what happens? If the sign here changes, then what happens? If the sign here changes, then what happens? Let's assume here is now plus. This other part will have plus. Now, the same thing, but the right hand side. This means x approaches A from the right. From the right hand side. Right hand side. From the right hand side. X approaches A from the right hand side. And the same thing here from the right hand side. X approaches A from the right hand side. So coming to this diagram here, we will now say not this side again, but instead we are interested in all x values that are on the right hand side and very close to the point A. So when you see this, then we are saying that x tends to the point A, but from the right hand side. X approaches A from the right hand side. So in like manner, if A is equal to 2, if A is equal to 2, then we are saying that using the graph, then we are saying that this point is 2. So from the right-hand side, will be, so meaning here will be 3, and maybe here will be 4. So very close to it, not all this one. This one will be far away. So we are saying very close to it. So we are talking about maybe 2.1. Somebody can say 2.05. Somebody can say 2.01. Yes, 2.001, 2.0001, and so on. You can see this one is very, very close. Very, very close as compared to this. This one is also very close as compared to this, and so on. So we're talking about those numbers that are very, very close to the point 2 that is in question, but from the right, based on the interpretation that we have gotten there. Now, what of in a case where no sign is given? Just say x tends to A. It means x approaches A from x, takes numbers, approaches A. We're talking about all x values. Sorry, let me use the word all x values. Okay, I can also use this. X approaches A from both the left-hand side and the right-hand side. Yes, it means x approaches A from both the left-hand side and the right-hand side. Or you say x tends to A from both the right and the left-hand side. So then we are saying that we are interested all x values that are in the neighborhood. Let me use that word here. All x values that are in the neighborhood of A. So this one now is different from the other one that we say all x values from that are very close to the point A, and all x values that are very from the right and from the left. This one we are saying a combination of both. So both this side and this side. So once you have this one is different from when we have the one from the left, or when we're considering the one for the right. So this one is considering the neighborhood, so both left and right. So as we have stated, if we say let A, that point A, be equal to 2, then we are saying that this one will be 1, this one will be 0. So we are saying that we are interested in all the values that tends to 2 from the left and also tends to 2 from the right. So these ones are for the right, whereas these ones are for the left. Just say 1.8, 1.9, 1.99, 1.999, and so on, and 1.9999, and so on. So the more you go, the more you get close to the point. So this is the neighborhood of 2, whereas this one is the right hand side, this one is the left hand side, as all approaches the point A. Now, when it happens, when you consider the limit from the left and it's going towards a particular point, as we have here 2, and if you go from the left and is going towards a particular point, and the point that all of them are going to or tending to is the same, then we say the limit exists of that function. We say the limit exists. Now, but if this one tends to a point different from this other side, then we say limit does not exist. Now, before we consider examples, let me also write this. Now, these that we have, let me say, let's say these that we have, let's say x tends to a from the left. X tends to a from the left. This we can also write as x is equal to a minus h. A minus h, where h here is a very small positive number, a minus h. H here is a very small positive number, and you can call it the step size. The step size. Now here h, based on what we have got before, when we say let a be equal to 2, then h can be 0.1, 0.01, 0.001, 0.0001. Now, when you subtract this from this, when it's 2, you begin to have this 1.9, 1.99, 1.999, and so on. So, you can write it in this way, and you can also write it this way. Now, this one we are saying that x approaches a from the left. And in like manner, we can also write x approaches a from the right as x is equal to a plus h, where we said this is the step size, where h is a positive number and can also be called the step size. The step size. So in this case, we are saying that x approaches a from the right-hand side. So if we say a is equal to 2, then we are saying that those numbers that are very close to 2. And from the example that we got, so in this case here now, that small number, that small positive number will be 0.1, will be 0.2, 0.01, 0.001, and by the time you add this to this, you will now be having those 2.1, 2.001, 2.001, and all the rest. You see that, and all these ones are also in the neighborhood of 2. So we are saying that if you don't see it this way, you can see this way. All of them means x tends to this number from the left, then we say x tends to this number from the right. Now let's consider an example to really illustrate what we have done. So for that of 2 that I have said, being that it talks about the neighborhood, the entire neighborhood, so then this x tends to 2 can also be written as x is contained in the neighborhood of 2 minus h and 2 plus h. Okay, then you say that you're talking about all x values in the neighborhood of 2. Now, let me give us a statement that will help us. Now, the limit of a function, say f of x, is a value that f of x approaches. The limit of a function f of x is a number that f of x approaches as x tends to a particular number. Let me write it. The limit of a function, the limit of a function, say f of x, is a number. Is a number. Let me call that number L. It's a number L that f of x approaches as x also tends to another number c. This is the same thing. Let me write it clearly. The limit of a function, say f of x, is a number L that f of x tends to as x also approaches c. As x also approaches c. Now, let's consider one example to further illustrate what I'm saying. But based on the earlier definition that I've given, this we can also write as the limit of a function is a number L as x approaches c from either the left, this one from the left, or you say the limit of a function is a number, say L, that f of x approaches as x also approaches c from the right, from the right. So this one that we have means as x approaches that number in the neighborhood of c, based on what I've taught you, because there is no sign there is no negative or positive sign. This one means strictly from the left, this one means strictly from the right, whereas this other one that we have is talking about the neighborhood of C. The neighborhood of C. So let's consider one example to see what we've been talking about. Let me give you graphically so that maybe you understand that one better. Graphically so that maybe you understand that one better. Now, if we have, say, this, let's say we have this, here is, say, 1, here is 2, here is 3, and we have a function that goes this way. This is a function, say f of x, it goes this way, it passes through that point 2, where here is 1, here is 2, here is 3, here is -1, here is -2, and so on. Here is -1, here is -2, and so on. Now this one, let me ask you a question. What's the limit of the function, of that function, as x tends to 0 from the left, and also the limits of the function as x tends to 0 from the right? Now, can somebody tell us this? Now, based on the explanation that I have given, is very clear. Now, we are interested in all x values that approaches 0, all x values that approaches 0 or tends to 0 from the left, from this side. Now, this is the function that we have. All x values that approaches 0. This is the point 0. This is the point 0. So the function as it gets close to approaches 0. So as it approaches 0 on the function, you see that is equal to, is tending to a point 2. As x goes towards 0 on the function, you see that it's going towards a point 2. So from the left-hand side, as the limit of the function as x tends to 0 from the left is equal to 2. Is equal to 2. Now, let's see from the right if it's the same. Now, as x tends to 0 from the right-hand side, that's the meaning, from the right-hand side, from this side now. Now, this is the function. As x tends to 0, f of x also tends to a particular number from the right, and that one is also 2. So you can see that the limit of the function is equal to 2 as x tends to 0 from the right. So you can see that both left and right, all of them are tending to a particular point 2. Then we say that the limit exists. A limit exists in this case because all of them are tending to a particular point. Now let me also illustrate with another graph so that we will enjoy the beauty. Let's say we have this. Let's say we have this, and this is a function. Let's consider this function where here is 0, here is this is the center point. The center point just say is pi over 2. Then here is pi, and so on, and so on. Now, if this corresponds to this place, and here is 1, and so on, from here to here, this height here is say 1. Then what is the limit? The limit of the function? The limit of the function, say f of x, where f of x in this case is sine x, as x tends to pi over 2 from the left. And what's also the limit of the function? The limit of the function sine x, as x tends to this point from the right. Or the limit. Now, this one that we have here now, if you test it, you will see that it's clear graphically. Now, as x tends to this point, you can see that on the function is going towards this maximum here. And the maximum corresponds to the point 1. Now, from the left. Now, from the right, as x also tends towards this side, you can see that on the function is also tending to a value 1. So this one is equal to 1, and this one is also equal to 1, based on the graph that we have. Then you say the limit exists. Then you say limit exists. Let me give you another one to further illustrate what we have said. Now, if we have a function, say, if we have a function where we have -1, -2, -3, we have 1, 2, we have 3, and so forth. We have, say, 1, 2, and 3. We have -1, we have -2, we have -3, and so forth. Now, if we have, say, if we have a number say from a function that is here is taken, here is not taken, that corresponds to this. Then if we have another number that corresponds to this, another function, where this point is taken, where this one is not taken. If we have another one that corresponds to this one, that corresponds to this one, where here is taken, and here is not taken, then we are interested in another one here, but here is taken up to this point, here is not taken for 1. Then we are interested in another one that is here up to this point. Here is taking. Then we are interested in another one that is here. Here is taking up to this point. Now look at this. The starting points are taken. This one is not taken. The starting point taken here is not taken. Starting point taken here is not taken. But now our interest, the limit of the function. The limit of the function, say f of x. What is the limit of f of the function as f of s tends to? What's that f of s tends to? As x tends to 2 from the left, let's say 2 from the left, and the limit of the function as what is it that f of s tends to as x also tends to 2 from the right. Now, based on what we have here now, let's look at this. As x tends to 2, this is 2. As x tends to 2 from the left, now the limit of the function, this is 2 here. So as x tends to 2, look at it. As x tends to 2 is this one. And it corresponds to a value 1. Okay? It's a constant function. As x tends to 2, it tends toward, as x tends to 2 on this side, this is the function. And it corresponds to 1. Now, as x tends to 2 again from the right, based on what we have, as x tends to 2 from the right, is this function. This is another function. Okay? And you see that it corresponds to another value equal to 2. Now, look at it. It's clear, it's pretty clear. As x tends to 2 from the left, this is 2. From the left is this side. This is the function, and it corresponds to a value, is a constant function, and it's 1. Now, from the right, which is this other one, you see that it's not this function again, it's another function that tends towards these 2 points, but from the right, and that one corresponds to another value, 2, and all of them are constant functions. Now, you see that this one tends to a different value. This one also tends to a different value. Then we say that limit doesn't exist, because we are saying that limit will exist if both from when you consider it from the neighborhood of that point, and all of them are tending to both left and right, all tending to the same point. Then you say limit exists. But this one, you can see that one is tending to 1, whereas the other one is tending to. So in this case, you say limit doesn't exist. Limit doesn't exist. Now let's based on this that we have, then somebody can say that finding the limit of a function simply means observing the tendency of the function as x approaches a particular point from both left and right. What are we saying? Based on the explanation that we have given, we are saying that finding the limit of a function simply means observing the tendency of the function when x approaches a particular value, both from the left and from the right. Now let's consider other examples algebraically. These are graphical examples, and we can really see how it moves. Now let's consider some examples so that we enjoy that. Now, if we say find the limit of the function, find the limits of the function, where the function, say f of x is equal to 2x plus 1, as x tends to 2. Find the limit of the function of that function as x tends to 2. So, based on the earlier statement that we have given, we are saying the limit of the function. What is it? As x tends to 2. Now, this one means in the neighborhood, both left and right. That's what we are asked to determine. Okay, so this is what we are about to do. Now, first of all, then this one means, as I've said, the neighborhood. So we have to consider it from the left, the limit of the function as x tends to 2 from the left is what? And the limit of the function as x tends to 2 from the right is what? That is our interest. That's the neighborhood. Now, what's the function? The function is 2x plus 1. Now, what are the values that are on the left as it tends to 2? One is on the left as it tends to 2 is 1.9. We have 1.99, 1.999. Now, when you put this here, you see that this one is approximately 4 plus this will give us about 4 points, some fractions, very close to 5. Here will be almost 4, okay? 3.99 something, that's what we will be having in this place. Very close to 4, very close to 4. Now, plus this will give us very close to 4. So plus this one will give us a 4.9 some fraction. Now, if you put this, you still have about 4.99 something. Maybe if you put this, you have 4.99. So you see that it's tending towards. So that's it. So from the left, if you use this to this, as I've earlier stated, you see that 2 times this will give us about 3 point some fractions, 9 something plus this will be 4.9. And this, if you use your calculator, you see that all of them are tending towards a particular point, say 5. Okay? Approximately 5. Now, when we consider it's approximately 5, so it's tending towards the point. The point here is 5. Now, when you consider this, what you will be having is the points here. So the points are this, just say this, 2.01, 2.001, 2.0001. If you consider this and you put it into this function here, the function 2x plus 1, then you will see that this one will give us 4.2 plus 1 will be about 5.2. Then when you come here, you see that you have 5.02. Here we'll have 5.002, 5.002. So you see that all of them are also, this one will give us just say 5.2. This one, if you put this value in, you're going to have 5.02, 5.02. Then this one will give us 5.002, 5.0002, and so on. So you don't see that all of them are also approximately 5. So both from the left and from the right, if you use your calculator, you will see the exact answer, but you now see that this one from the left is also tending towards a particular point, which is 5, and this one from the right is also tending towards a particular point, which is also 5. So we are saying that after checking the neighborhood of 2, then we are saying that f of x is approaching 5 as x tends to 2 from both the left and the right. Now, some might be tempted to say, why don't we impute the exact number 2 instead of considering the neighborhood? Yes, sometimes you can do that, but it's advisable you consider it in the neighborhood, because there are some functions that when you impute the exact number, it will the system will vanish. Sometimes it will make it undefined, and so on. Okay? But if you consider the neighborhood, you will see that the function limit exists. So in this case here now, both from the left and right, you will see that all of them are tending towards 5. So we say limit exists in this case. Now let's consider this. let's consider another one where the function that we have is x squared minus 1 all over x minus 1. As x tends to 1, but not equal to 1. Tends to 1, but not equal to 1. Because once, like in this case here now, based on that question, if x takes 1 here now, this under will be 0 straight away. The under will be 0 straight away, and we don't want that kind of a case. So there is need for us to consider the neighborhood to see if it really exists. And there are some that you don't just dive into them by substituting the value, but rather you try to go through some mathematical joggings by simplifying it. Once you simplify it, you see that it will come out straight away. However, in this case, what are the cases that we are considering? Both the left-hand side and the right-hand side. When you consider what you will be having is this other side you have 0.9, 0.99, 0.99, the left hand side 0.999. Whereas the right hand side you have 1.1 or yes 1.01, say 1.001, 1.000001. So these are the values that you have on the right hand side, whereas these ones are the ones that are very close to 1 from the left hand side. Now, if you put these into this expression, and when you simplify, you see that the limit of f of x, where this is f of x, as x tends to 1, will be what? Now you will see that when you consider this side, you will see that it will be going towards approaching 2. It will be approaching 2. I want the class to check that to ensure that it's correct. And in like manner, when you put this, it will also from the left, then from the right, the limit of the function from the right as x tends to 1 from the right, you see that this one is also approaching 2, is also approaching 2. Now, another simple way to make it clearer, I have said that the audience should please check that to ensure that what we are saying is correct. However, given this function, say f of x is equal to this minus 1 all over x minus 1. This you can further simplify as x plus 1 into x minus 1. This thing is same as this all over x minus 1. We are saying the same because this times this will give you this times this will give you negative x, this times this will give you positive x. So the negative x and positive x is off the job market, and this times this will give you negative 1, which is this. So now when you simplify it in this way, this one is off the job market, so that you will only be left with f of x is equal to x plus 1. X plus 1. So when you impute this into this one now, is now clear. You can now see that you have 1.9. Okay, going towards 2. When you have this, you have 1.99. 1.99. When you put this, you have 1.999. You see that all of them is approaching 2. Now, in like manner, when you consider this one, when you put this, you are going to have 2.1. Now, when you put that, you have 2.01. When you have the other one, you have 2.0. So you see that all of them, both from the left and right, is tending towards the point 2. So we are saying that the limit of that function as x tends to 1, as x approaches 1, f of x approaches 2. F of x approaches 2. F of x approaches 2. The limit of the function as x approaches 1, we are saying that f of x approaches 2. So limits also exist in this case. Limits also exist in this case. Now, let's consider another one. Let's consider another one. So if we are asked to find the limits if we are asked to find the limit where f of x is sine x all over x, sine x all over x as x approaches 0. As x approaches 0, where x is measured in radians. Where x is measured in radians. Where x is measured in radians. Now, when you check this, as x approaches 0, so the points that we'll be considering are plus or minus 0.1, the plus or minus 0.1, and so on, plus or minus 0.01, 0.001, and so on, plus or minus, because the left hand side will give you negative towards it, then this other side will give you positive values towards it. So you say 0.01, then you have plus or minus 0.001, and so on, and so on, and so on. So when you substitute all that into that function, you see that both from the left and right hand side, you see that the limit of the function, that function as x tends to 0 will be equal to 1. Will be equal to 1. I want the class to also check that and tell us how it is. Now, what if the function is this, where as x tends to the limit of the function as x tends to 0, as x tends to 0. What happens? Remember, these are the things that we will still be considering. So when you put it, the negative side, you see that the values that we will be having will be negative values. In that one, we have said that the limit exists. Now, for this very case, when you put this one here, the left-hand side, you see that negative values will begin to pop up. Okay? It will begin to pop up. Now, when you go for the right-hand side, because the values that you will be having will be positive. So you see that they are not approaching a particular point, because one is approaching, one side will be approaching negative value, whereas the other side will be approaching positive value. So in this case, we say limit doesn't exist as x tends to 0. Now let's quickly give a definition so that we may really, if we're asked to do that, we'll do that with comfort. And with the explanation that we have gotten, at least, I believe strongly that everybody or majority of the people will be able to say something when it comes to the limit of a function. Now let's say definition. Let's see be a point. Let's see be a point in some interval, say I, of the real line, let f be a function, let f be a function which is defined at every point of I except at the points C. Then the limit the limit of the function f as x approaches c is L, written as the limit of the function is equal to L as x approaches c. As x approaches c. If for any positive number, say epsilon, there is some number, say delta, greater than 0, such that the absolute value of the function f of x minus L is less than epsilon for all 0 less than the absolute value of x minus c less than delta. Now this is a definition that helps us. We are saying that the limit of a function, this exists. Okay, the limit of the function where f of x tends to this as x approaches this, it exists. If for any positive number, say epsilon, there exists some number delta such that this, the absolute value of this, is less than this for all 0 less than this, less than this. Now, if we are given problem, all that we need to do is to determine the value of delta, ensuring that epsilon is also positive. Now, let's consider some critical examples to demonstrate this definition that we have given. To demonstrate this, remember this part that we have. We are saying that the limit of a function f of x equal to L for x tends to this, if this occurs if for any positive number epsilon, there is some number, say delta, such that the absolute value of f of x minus L is less than epsilon for all 0 less than the absolute value of that, less than delta. Now let's consider some examples to illustrate what we have. Now say prove that, let's say, prove that 1, the limit of this function 3x minus 4 is equal to 14, where x tends to 6. 2, let's say, the limit of the function, where the function that we have is 2x minus 1 is equal to 3 as x tends to 2. Let's consider 3. We are saying the limit of the function, now in this case the function is absolute value of x is equal to absolute value of c as x tends to c. Then let's consider another one, different type. Let's say the limit of the function f of x, where in this case f of x is a piecewise function where we have -1. X is less than 0 and 1 for x is greater than 0. Now, for us to demonstrate the definition that we have given using this example, we are saying that prove that the limit of the function, that function is called 14 when x tends to 6. Now, the first case, this we can do. As I have stated earlier, I said all that we do is to ensure that we find the value of delta, making sure that epsilon is positive. Making sure that epsilon is positive. So this we can do. But remember the definition. We said for any positive number, epsilon, this statement is very important. But first of all, let's consider this part, such that this one holds. Now we are saying that the absolute value of f of x and f of x is equal to, say, the absolute value of f of x is minus L. And this is equal to the absolute value of f of x, where f of x is 3x minus 4. That's for f of x minus L. Where is L? This is our L based on the definition that we gave. So L will be equal to 14. L is equal to 14. That is what we have. In this other part. Now, if you simplify this we can also still write as this one minus 4 minus this will give you 18. So you say 3x minus 18. That's what we have. So this you can factor something out and you see that that is reasonable. Now, if you factor that, we are going to have, if we try to factor something out, you will see that we are going to have the absolute value of, say, 3 into x minus 6. That's what we have. And you can take the separate absolute values. Then this one will come out. Absolute value of a number is that number. So you say 3, the absolute value of x minus 6. That's what you have here. I have simplified it. Then let's come to this other part. Now this other part is saying that where x, the absolute value of x, okay, x minus c. Now what is c? C is this, based on the definition that we gave. The definition we gave was, look at it, we say the limit of the function f of x is equal to L, where we say x as x tends to c. That was what we gave from the definition. So c in that case now is c. So 6. So we say x, from here we say x minus 6. That's what we have. X minus 6. That's what we have. Now, this statement is for epsilon. Whereas this statement here is for this delta. Okay? So you can see that the one for the delta is also contained in that of L. So in this place here now, we can say that based on this, we are now saying that in place of this, we now have, in place of that, we now have 3 absolute value of x minus 6, which is this one for the delta. Okay, whereas this entire thing is for epsilon, is equal to epsilon, where this one is the delta. So you say 3 delta will be equal to this. So you say delta will be equal to epsilon over 3. Or you say 1 all over 3 epsilon. That's what you have. So going back to the statement that we have, then one can comfortably then write that for any positive number epsilon, there exists some number, say that such that this one is less than this, for all values less than, in place of this, we now put this, where we have 1 all over 3 epsilon. That is what we have. Because I have said, for us to be able to get to demonstrate what the definition really meant, all that we do is to determine the value of delta, which we have done. Now, in like manner, we can also try other ones using the same method, and you will see that life is pretty simple. Now, based on these that we have done, we can also do similar things. Now, from here, it is also pretty simple. Okay, these ones are f of x minus L. That's what we have. So minus is coming here. So if minus comes here, minus 3 minus 1 will give this one minus 4. So minus 2 minus 4, that's what we have. So you can factor 2 out. Okay, then you are going to have, if you factor 2 out, you are going to have x minus 2. That's what you will be having. The absolute value of x minus 2, that's what you have. Now, when you consider this other part, you have x minus c. Now, where c is equal to 2. So you now see that this delta is also looking at the other part as we have in part of the epsilon. So the answer to this one is also pretty simple. Is also pretty simple. This other one, following the same method, we will have 2 x minus 2, that's what we have, is equal to this, where this one is also our delta. So you say this one delta is equal to epsilon. So you say delta is equal to 1 over 2 epsilon. So in place of this, in place of delta, this is what we have for this case. So I want you to check it to ensure that what we have written is also correct. I want you to check it to ensure that what we have written is also correct. Now, 3 is also, example 3 is also very simple and straight away, and I will want the audience to do it. Now, in all the first and the second one is clear that the limit really exists. Now, the fourth one is the one that I would really want to look at it. I will really want to look at, but it's also pretty simple. It's also pretty simple. Pretty simple in the sense that there is no cause for alarm in this one. Look at it. This function, when x is less than, so when x is less than 0, then we are considering the left-hand side limit. We are considering the left-hand side limit. Now, this function when x is greater than, which is the right-hand side limit, I now see that when considering the left-hand side limit of this function, you now see that the value is -1. Whereas when you consider the right-hand side, you see that the value is +1. So limit doesn't exist. They don't tend to a particular number. So for this case, you say limit doesn't exist. Limit doesn't. This one limit exists, we have shown. This one also limit also exists. This one limit also exists, even if I have not shown, but I want the class to do it. But this one also shows that limit doesn't exist. Limit doesn't exist. So I would want the audience to look at those simple cases to help your understanding in what we have done. Now let me give you, these ones I won't solve, but let me give you some examples so that we can enjoy life. So that we can enjoy life. Now, if we have evaluate, say evaluate the limit as x tends to 1 of this function, where the function is x raised to the power 2 x minus 1. Evaluate it. Evaluate. Now, I'm saying also evaluate this other one, limit of the function as x tends to 2 of 3x minus 7 all over x squared minus 4. Evaluate that. Then, lastly, let's also evaluate the limits of the function 5 all over x as this tends to as x tends to 0. Now, when you consider all these ones, I want you to check it. When you consider all these ones, you see that these ones does not converge. It doesn't go. It doesn't arrive at a particular answer. when you check them from both left, right, and center. So in all this one, you say all fails to exist. To exist. Limit doesn't exist in all this one. I want the class to go and check them out. Then you will see that it doesn't exist. Now there are other pretty simple cases that we might consider maybe in our next class as we go on. But in overall, we are saying that when you say consider the limit of the function, we're interested in considering them by looking at the values of x close to that point, both from the left and both from the left hand side and the right hand side, which is the neighborhood of that point, and that is what we have said. And we said the limit of the function f of x is equal to a number that f of x tends to, as x also tends to another number. With this explanation that we have given, at least I know that you have gotten an understanding that will enable you to determine if limit exists in a particular function or not. And when you are asked to evaluate, like this one that I've shown, it's just pretty very clear. It's just pretty very clear that in all these ones, when you evaluate at this point, in what sense evaluate? When you evaluate at those points, you see that all these ones doesn't also exist. Thank you and God bless you as we continue with these limits and continuity in our next class.